So next talk is gonna be given by Ariana Diogene. She is from University of Florence, and well, it's a joint work with Massimo. And she's gonna talk about curves with large automorphism groups.
Thank you. Thank you for the introduction. And in this report, I'm going to present a joint work with Massimo Giulietti on curves with large automorphism groups. And in particular, we studied the case of curves admitting a dihedral automorphism group. Okay. Thanks. Okay. Okay. The case of curves admitting a dihedral automorphism groups, curves with non-perfect automorphism groups, and curves with abelian groups. Okay. First of all, let me fix the notation for this introductory part. So, as usual, by curve, I mean a projective, geometrically reducible, non-singular algebraic curve embedded in some projective space over the base field K. And we are supposing that K is an algebraically closed field, but for the moment, we are not assuming any restriction on the characteristic, even though the main target of the present talk will be algebraic curves in positive characteristic. G or G of X is the genus of the curve, and out of X denotes the automorphism group of X, where an automorphism of a curve is just a birational map from the curve onto itself, that is, roughly speaking, an invertible map defined in homogeneous coordinates by homogeneous polynomials of the same degree. And as Maria told before, curves with genus smaller than 2 have an infinite automorphism group. And they are the only exception, since any other curve has just a finite number of automorphisms. When a curve has many automorphisms, it is particularly interesting because other curves can be constructed from it and can inherit important properties of the starting curve. These curves are called quotient curve of X. And now I'm not going to give you the precise definition of what a quotient curve is. I'm just going to recall that for a non-trivial finite automorphism group, say G, its action on the points of X is faithful, and there exists a curve denoted by X over G, and that is called quotient curve of X by G, whose points correspond to the orbits of X under the action of G. And in fact, there exists a natural morphism from the starting curve onto the quotient curve, where 2 points have the same image if and only if they lie in the same G orbit. And as matter of notation, we denote by omega the short orbits of this action. We also have the famous relationship between the genus of a curve and that of the quotient curve, provided by the Riemann-Hurwitz genus formula. And an important feature of this formula is that in the case of zero characteristic, or in the case where the characteristic does not divide the order of the stabilizer of any point, the different, that is, the last part of this formula, depends only on the action of the elements of the group. And in fact, the contribution of each point to the different is just the size of the stabilizer minus 1, and the formula can be read in this way. Okay. And let me briefly discuss the problems which have received much attention in the last few years and for which substantial progress has been made. And first, to bound the sides of the automorphism groups of curves under some conditions on the invariant of the curve, or under some conditions on the abstract properties of the group. Then to classify curves whose automorphism groups attains the bound or are close to the bound. And finally, to classify groups of significant classes of curves. And let me now recall some recent results. In 2020, Korchmaros and Montanucci dealt with the case of the groups where D is a prime different from the characteristic. In 2022, Ambar and Gunesh proved some bounds for nilpotent groups. Arakelian and Speziali completed the classical work by Homma and characterized in 2021 curves with large automorphism groups of prime order. In 2021, Lee and Timpanella showed some interesting bounds for the size of the stabilizer of a point. And more recently, together with Massimo Giulietti and Marco Timpanella, we classified curves with an automorphism group that is cyclic and large with respect to the genus. The aim of this work is to investigate curves that have dihedral automorphism group, a non-perfect automorphism group, or an abelian group, but always under the hypothesis that the group is large with respect to the genus. And in fact, the main goal is to extend results that are somehow classical for the case of Riemann surfaces, that is the case where the field is the complex field, to the case of positive characteristic. And the difficulty is that topological methods cannot be used, and so a purely algebraic approach is needed. And here we have an example of a result that is classical and valid for Riemann surfaces, but cannot be easily extended to the case of positive characteristic. So if we have a Riemann surface of genus greater than or equal to 2, and if we call G a group of automorphisms, and if we denote by K the number of short orbits and by prime G the genus of the quotient S over G, we have that the group G is generated by these elements under these conditions on AI, BI, and XI. And let me recall that for two elements of a group, say A and B, the commutator of these two is the element A, inverse of A times inverse of B times A times B. Okay. Let me now start with the dihedral case, where known results are proved for Riemann surfaces are proved by Gromasky, McLachlan, and others. And let me introduce our setting, where we consider a curve under the same hypothesis of the first slide. But now we assume that the characteristic is positive, and in particular that is even. It is odd, sorry. And we denote by H the dihedral group of automorphisms, and by G the cyclic subgroup of H of index 2. N is the order of G, and we assume that N and P are coprime, and that N is greater than 2 in order to exclude the abelian case. Here we have some preliminary results, some facts that we showed. So first, the fact that if we have a short orbit under the action of G, say gamma, there are just two possibilities for it. Or gamma is still an orbit under the action of H, or there exists another orbit of the same length of gamma, such that the union of these two is an orbit under the action of H. And in particular, the short orbits of the under the action of G are of the second type, and this means that there are an even number of short orbits under the action of G. Then we show that if N is greater than or equal to G minus 1, there are at least two short orbits under the action of G. And when N is greater than G plus 1, the quotient curve X over G over H has genus equal to 0. Another important tool was this theorem, which states that if we denote by T the number of short orbits under the action of H of length exactly N, and by K the number of short orbits of length smaller than N, if we assume that K is greater than or equal to 1 and N is strictly greater than G plus 1, we have that for each point of the K short orbits, the stabilizer in H is the unique cyclic subgroup of G of size 2 times N over the length of the short orbit omega I. Also that there are at least two short orbits under the action of H of length exactly N, and in particular when N is odd, T is even. Finally, in the case where T is equal to 2 or T is equal to 3, we have an easy way to compute N. Okay, at this point, we divided our study into cases. The case where K is equal to 0 and the case where K is greater than or equal to 1. For the case K equal to 0, we obtain that if N is greater than G plus 1, then the order of the dihedral group is 4 times the genus minus 4, and N is divisible by 4. And also we have these equations for the curve. While for the case k greater than or equal to 1, again under the hypothesis that n is greater than g plus 1, we have just 3 possibilities, but in each of them we have 4 short orbits, both under the action of h and g. Okay, the first case is that the order of h is exactly 4 times the genus plus 4, and there are 3 short orbits under the action of h of length exactly n and 1 short orbit of length smaller than n. The genus is even and the curve is hyperelliptic, and we have an example for this case. The second case is similar, but now the order of h is 4 times the genus, and the genus is odd. The curve is again hyperelliptic, and also for this case we have an example. Finally, the last case, we have 2 short orbits under the action of h of length exactly n, and 2 short orbits of length smaller than n. And in this case, the order of h depends on the ramification indices of the 2 short orbits of length smaller than n. And let me quickly show a sketch of the proof of this theorem, where we denote by omega the number of short orbits under the action of h, and by n the number of short orbits under the action of g, while tilde g denotes the genus of the quotient curve x over g. Okay, first of all, we found all the possibilities for the pair k and t, and so we have that it can be only 1 and 3, 1 and 4, 2 and 2, and 2 and 3. And since omega is the sum of k and t, we have that omega can be only 4 or 5. Then we studied the quotient curve x over g, and we obtained that it can be only elliptic or rational. And by studying the Riemann-Hurwitz formula with respect to g, and by recalling that there is an even number of short orbits under the action of g, we have that n can be only 2, 4, or 6. And in particular, the quotient curve can be elliptic only when n is equal to 2. At this point, we compared the Riemann-Hurwitz formula with respect to g and h, and after ruling out the cases which led to contradiction, we obtained that the only possibility is that omega and n are equal both to 4, and in particular, when k and t are 1 and 3 and the genus is given, we have the first case of the theorem. When g is odd, we have the second case, and finally, when k and t is both equal to 2, we have the third case of the theorem. Okay, let's now move on the non-perfect case, where known results for Riemann surfaces are proved by Setilla and Gromasky. And first, let me quickly recall what is a non-perfect group. Earlier, we saw the definition of the commutator of 2 elements. And if we consider the subgroup of G generated by the commutator of each pair of elements, it is called the derived subgroup of G, and it is denoted by prime G. Well, when this subgroup coincides with G, the group is called perfect, and consequently the group G is non-perfect when the derived subgroup is a proper subgroup. And for the non-perfect case, first we found a bound for the size of the group, but just in the tame case. And we have that the bound is 48 times the genus minus 1, and there are actually curves which attain this bound, so it is a really bound. And these curves are, for example, the Fermat curve of degree 4 in a characteristic greater than 3, which has genus equal to 3, and admits a non-perfect automorphism group of order 96, that is 48 times the genus minus 1, or the Bolza curve in positive characteristic, which has genus equal to 2 and has a non-perfect automorphism group of order 48. Okay, then we showed that if we have a curve of genus greater than or equal to 2 defined over a field in positive characteristic, if the curve has a non-perfect automorphism groups, then for each prime different from the characteristic, there exists a curve of genus prime G, such that prime G minus 1 is equal to D to 2 times G minus 1, which has still a non-perfect automorphism group of order D to 2 times G times the order of G. And a direct corollary of this theorem is that in odd characteristic there exists an infinite number of curves with genus that goes to infinity, which has a non-perfect automorphism group which attains the bound 48 times the genus minus 1. And to prove this corollary, it is sufficient to consider the Fermat curve of degree 4 or the Boltzmann curve and to apply the previous theorem. And let me quickly go through the main step of the theorem of the proof of the theorem. So we denote by M the function field of X and by F the fixed field of G. Thanks to a known result, we have that there exists a unique and ramified elementary abelian extension of F of degree D to 2 times G, and we call it L. Then we show that the extension L over F is a Galois extension. Now, the Galois group of the extension L over M is normal in the Galois group of the extension L over F, and the factor group is isomorphic to the Galois group of the extension M over F, that is G by definition, and that is non-perfect by hypothesis. Then it can be proved that also the Galois group of the extension L over F is non-perfect. And let me conclude with the abelian case, where known results for Riemann surfaces are proved by Lomuto, Pignatelli, and Raso. And we are studying the case of curves of genus greater than or equal to 2, which has an abelian group of order coprime with P, and where the order is greater than or equal to 2 times the genus minus 2. And clearly we have the famous bound provided by Nakajima, that is 4 times the genus plus 4 in general, and 4 times the genus plus 2 in the case of even characteristic. And first, we showed that if we denote by K the number of short orbits under the action of G, and by Ni the order of G over the sides of the short orbit omega I, then if the quotient with respect to G is rational, then the group G is isomorphic to a quotient of this external product, where we have the omission of the group zeta and I0. And then we found a list of all the possibilities for the ramification indices of the short orbits under the action of G. And about the future, we would like to continue the study of the dihedral case, and in particular, we want to investigate the non-tame case for dihedral groups. And also, we are trying to find all the possibilities for the groups in the abelian case. And this is all I wanted to say, so thank you for your attention.
Thank you, Ariana, for the nice talk. So, questions, comments? So, yeah, one question should be like, you worked everything for the dihedral group, but why this group? You have so many groups. And
What, sorry?
You have worked everything for the dihedral group, but you have other groups, like...
Yes.
So...
yes, in the moment, for the dihedral group, yes, it's all, but...
No, your motivation about choosing this group. Like,
okay, because we studied the case of cyclic subgroup, or of cyclic group, so we hope that the results that we get for cyclic group can help us in the study of the dihedral groups, and so we try to do a similar study for this case.
Yeah, thank you. So let's thank her again. Yeah. So we have 4 minutes for the next talk, okay? So you can go for a coffee, maybe.
Essa primeira acho que quase não mudou.
Mas o resto bagunçou muito.
Oh. If I agree, okay. Now I understand that. Just it. He just gave a talk about this. Maybe we should see. Bunch of those. Okay, so now we go to the last talk of the morning. So Lorenzo Beninati is going, he's from University of Toulon, and he's going to talk about explicit formulas for the number of rational points on singular curves over finite fields.
So thank you for being here. It's a real pleasure for me to be here today, so I'd like to thank the organizers for giving me this opportunity. So yeah, today I will talk about singular curves and the results we obtained about their number of rational points with my PhD supervisors Yves Aubry and Fabien Herbeau. So I'll start by recalling some definitions and background about curves and their rational points. So for the moment, when I will talk about curve, it will stand for an absolutely irreducible projective algebraic curve defined over Fq and of genus G. And for the moment, I will also suppose that the curve is smooth. A rational point of such a curve over Fq to the R is simply a point whose coordinates lie in Fq to the R. And we'll denote by NR the number of rational points of the curve over Fq to the R. And so what we'll be interested in is, given a curve, what are actually this number of rational points? So thanks to Veil, we know exactly the expression of these values. We have the following formula, which says that the NR are equal to Q to the R plus 1 minus a sum of complex numbers that are algebraic integers satisfying the Riemann hypothesis. The problem is that, in general, given a curve, we do not know what are these algebraic numbers. So what we are going to do instead is trying to find bound in order to estimate these values. So with all this information, we can get a first bound, which is the Veil bound, also known as the As-Veil bound, which says that the number of rational points is bounded by Q plus 1 plus 2G square root of Q. Unfortunately, this bound is not optimal in general. It was first noticed by Ihara using the fact that N2 is bigger than N1. And he also gave another bound, which happened to be sharper than the Veil's bound as soon as G becomes greater than a certain quantity depending only on Q. So we have this phenomenon. The more G grows, the more our bounds are far from being optimal. We saw already that it's true for the Veil's bound, but one can also prove the same thing for the Ihara's bound. So one could ask, what happens if we let G tend to infinity? Do we have bound at infinity? Well, for that, let me define the quantity NQG, which is simply the maximum number of rational points you can expect when you fix Q and G. Then we define the ERAS quantity to be the limit sub of NQG over G. And then we have a bound for this quantity, namely the Dirichlet-Vladuc bound, which says that AQ is bounded by square root of Q minus 1. And when Q is a square, we even have an equality, which means that this bound is sharp. Okay, so now that we know about this bound, let me talk about the Serre explicit formulas, which is a method that provide infinite families of bounds for the number of rational points. So the idea is the following. Consider a trigonometric polynomial of this form, to which we associate the polynomial psi t and psi dt. Then Serre tells us that for any trigonometric polynomial of this form, and for any curve defined over Fq of genus G, we have this following equality, named the explicit formula. So here, the theta j's are just the argument of the omega j's, as before, and Bg denote the number of close points of degree G of the curve. So this equality is not useful in practice, but now, if you assume that the polynomial is doubly positive, then the previous equality becomes an inequality. We can give an inequality, which gives us a bound for our number of rational points. And this bound depends only on the choice you made for your trigonometric polynomial. So now the goal is to find the best polynomial that will give you the best bound for your curve. So let's do some examples. If you take first the simplest polynomial you can take, 1 plus cosine theta, then with the previous inequality, we recover the Weyl bound. Now, if you take all the coefficients of your polynomials to be equal to 1, and you divide the previous inequality by G to get the value at infinity, we recover, this time, the Dirichlet-Vladuc bound. So with this method, with this quite easy polynomial, we can recover the best bound we know. And in practice, it's a very powerful tool, because using other polynomial, we can estimate really precisely some values for NQG. Okay, so now that we talk about that, I would like to move on singular curves. So now I will still consider the same property for our curve, but this time we allow us the possibility to work with singular curves. So singular curves are curves with singular points, and the property of singularity of a point can be seen as a property of its local ring. We have that a point is non-singular if and only if its local ring is equal to its integral closure. Then we can define its singularity degree to be the dimension of the constant ring OP bar over OP as a FQ vector space. And in particular, we have that delta P is equal to 0 if and only if the point is non-singular. And what we are interested in is, as before, what are the number of rational points of such a curve. So, we define also the quantity delta to be the sum of all the singularity degrees. This is well defined because the number of singular points is always finite. And then we define the arithmetic genus of the curve, which is denoted pi, to be the geometric genus G plus delta. And so what we are interested in is the number of rational points of such curves. So in this case, we also have a formula given by Aubry and Perret. So here, the omega j's are the same as before, but now we have a new term that appears, which is a sum of complex number of modulus 1. And again, we do not know about these omega j's, and we do not know neither about these beta j's. But with all this information, we can get a first bound, which is known as the Aubry-Perret bound. And it can be seen as a generalization of the Weyl bound, since if you take pi to be equals to G, we are in the smooth case, and then we recover the Weyl bound. So now a natural question arises. Is it possible to extend the Serre's explicit formula to possibly singular curves? A first reason is that we know that it's a powerful tool in a smooth case, so why not in the singular case? And then, except the Aubry-Perret bound, we do not know explicit bounds in general for singular curves. So it would be a good way to obtain it. Well, the answer to this question is yes. And a first way to see it is by using a result from Aubry and Perret, which says that the difference between the number of points of our singular curve and the number of points of the normalization of the singular curve is less than pi minus g. And then what we can do is just using the Serre explicit formula on the normalization of the curve, and we get a first explicit formula for our singular curve. But here we are a bit disappointed because we have only used the explicit formulas on the smooth part. We didn't take into account the singular part of the curve. So is it possible to do it? Again, the answer is yes. In the same paper, Aubry and Perret propose another explicit formula, which take into account the singular part of the curve. But when we compare the two bounds, it happens that this bound is not better than the previous one in general cases. So we are still a bit disappointed. For example, if we take back the polynomial 1 plus cosine theta, with the previous inequality, we recover the Aubry-Perret bound, like in the smooth case. But with this inequality above, we obtain something that is less good than the Aubry-Perret bound. So now let me talk about our result, which is a new explicit formula for singular curves, which happens to be better than the one proposed by Aubry and Perret, and which is often better than what we can call the trivial one. So here we kind of fix the problem of the one proposed by Aubry and Perret. So let me show you a quick example to see how it can be useful. So let's consider a curve defined over F2 with g equals 4 and pi equals 5. Then if we use the Aubry-Perret bound, we know that the number of rational points over F2 is bounded by 15. And then using our result with this polynomial, we know that actually it is bounded by 8. So let me talk about the proof quickly. So we use first a formula which is a relation between the number of closed points of the curve and the number of rational points. Since we know exactly the expression of the rational point, we can obtain the second equality. And then what to do, we multiply both sides by this quantity, and we sum over n to get the polynomial, the trigonometric polynomial appears. So here, what we can see is all the terms are real except the last one. So we can only consider the real part in the last sum. And now the tricky part is to estimate efficiently every term in the sum in order to get a good bound. And to do this, we used results on the Poisson kernel and the harmonic function. And we can show that all the terms here are bounded by 1 over square root of q plus 1. And then we obtain the result using the fact that this delta x, I didn't talk about it, but it's bounded by pi minus g. Okay, so now we want to use this explicit formula for singular curves in order to get values for nqg pi. So this quantity is defined as the analog of nqg, but in the singular case. So it's the number of rational points, the maximum number of rational points you can expect for q, g, and pi fixed. And for example, in the last example, we worked over F2 with a curve with genus 4 and 5. So what we show is that n2 for 5 is bounded by 8. But in some cases, we can even do better. We can obtain exact value. So using the explicit formula and the fact that nqg is bounded by nqg pi, we can obtain several exact value. So here is an non-exhaustive list of exact value you can obtain just by using a good polynomial and the fact that nqg pi is bounded by nqg. Enfin, the inverse, sorry. Okay, but there are other ways to obtain exact value, and that's what I would like to talk about now. So to study the quantity nq2 pi, sorry, so I will be treating the case where g equals 2 with other methods to show you that how we can obtain other exact values. So here we'll need two tools. The first one is the quantity nq2, which has been completely studied by Serre. And we also need an explicit construction of singular curves with many rational points, which was proposed by Aubry and Yizzi, and which depends on the number of close points of your curve, of a smooth curve. So typically, their construction gives the following theorem. So let's consider a singular curve defined over Fq with geometric genus G and arithmetic genus pi. Then we know that its number of rational points is exactly nqg plus pi minus g, if and only if its normalization as nqg rational point and pi minus g has to be less than this quantity, which is the maximum number of degree 2 points on the set of smooth optimal curves defined over Fq and of genus G. So here, an optimal curve is a smooth curve which has nqg point. And so using this theorem and results of Serre, we have treated the case where g equals 2. So we had to treat different cases depending on the value of q. For example, we have to treat the case where q is said to be special. That means that he is not a square and he has to satisfy one of the following properties. Okay, so we managed to treat the case where g equals 2. So first, when q is a square, so we have exact value for this quantity. And then if q is not a square, then you will have to treat whether q is special or non-special. And if q is special, you have to be aware of the fractional part of 2 square root of q. And just to give you an idea of the proof, so for each case, we have to find a curve with the maximum number of close points of degree 2 among the curve with exactly nq2 rational point. So that implies to know what is exactly this maximum number. And this can be done by studying the defect of such curves and using result on the Jacobian. And then once we have this curve, we have to construct from this curve a singular one. And it can be possible by using the construction of Aubry and Yezi. Okay, so for the last minutes I have, I'd like to do an example to show you that actually it's possible to combine the two methods in order to get bound for nqg pi, but also to obtain information from the smooth curve by studying the singular curve. So let's take q equals 2 and g equals 3. So using the explicit formula for singular curve as before, we can get the following bound. So here I've used the same polynomial as I showed you before. Now we know that in the smooth case, n23 is equal to 7. So what we can deduce is that n234 is also equal to 7. This means that if you consider a smooth curve defined over F2 with genus 3, which has 7 rational points, then its number of degree 2 points has to be 0. And this comes from the construction of Aubry and Yezi, because if we suppose that there exists at least 1 point of degree 2, then one could construct from their construction, one could construct a singular curve which contradicts this inequality here. And with the same argument, we can say that the number of degree 3 of the curve has to be 0 or 1. So in terms of rational points, we have that we have 7 rational points over F2 and F4, and we have 7 or 10 points over F8. And now, using these 3 equalities, we can solve the system, the following system, in alpha 1, alpha 2, alpha 3, where alpha I is defined to be omega I plus its conjugate over 2 square root of 2. And when you solve this system, up to permutation, we have this solution. The problem is that using a result on the indecomposability of the Jacobian, we know that this case of alpha, for alpha 1, alpha 2, alpha 3, do not correspond to the case of a curve. So our assumption has to be false, and then we know that the number of rational points is 10. And so what we showed is that the previous inequalities are equalities. So we obtain exact value for the quantity nqg pi. But what we showed also is, since we know that the number of rational points over F8 is 10, one could solve the previous system, but this time you suppose that the number of points over F8 is 10. And so you obtain the exact value for alpha 1, alpha 2, alpha 3, and so for the omegas j. And remember what I said at the beginning, that's the value we want, because since when you have these values, you know all the values for the number of rational points on any extension. Okay, so thank you. That's all for me.
So thank you for the nice talk. So questions, comments? Well, I have a question then. You have your example on slide 14, for example, because you have chosen psi something in no, next one, I think 14. No, okay. The example you have that one. Yeah, that one.
Yes.
So, I mean, what is the idea to choose your? You have to choose a special psi to get better bound. So, what is the idea?
What I didn't mention is in the smooth case, the problem of finding the best polynomial that will give you the best bound is it's an optimization problem, and it has been completely solved by Osterle. It's here. So he completely optimized the problem, and he gave for if you fix the number of points, he gives you the expression of the polynomial that will give you the best minimizing solution for G. So it's kind of the opposite problem, but it's the same. And using this optimization, what we can do is find, if you fix the number of coefficients that are non-zero, you can find what is the best polynomial to choose. So if you take only one coefficient, it will give you the Weil bound. If you fix two coefficients to be non-zero, you have this polynomial, and so on. And if you do it at infinity, you will recover the Drinfeld bound.
Second question. Did you compare your bounds? Like Roma has some papers on bounds about exactly the number of rational points on singular curves. So did you compare with some known bounds?
No.
No, not yet. Okay. Thank you.
Thank you.
Hello. So just a quick announcement. Just to let you know, for those of you who haven't decided where to go for lunch, two members of our team, and in this case, Tiago, I mean, at least for today, he will be going to this. Yeah, there is this place called this restaurant called Mamãe Natureza. It's, I mean, very very close. If you are more from the vegetarian side, it's a very good option. João, who is also here, he'll also show you our cafeteria here on campus. I mean, it's a few steps to the left if you want to get something simpler. And also Leonardo, who is in the other room, he's going to another restaurant. If you are more into, let's say, meat, and not vegetarian, Leonardo is the guy to talk to. So and the three of you are gonna gather people outside, like in maybe within the next 5 minutes. And one more thing, if you want to leave, okay, the auditorium will be open during the lunchtime. So if you want to leave your stuff here, it's okay, but you won't take any responsibility for that. But I mean, just to let you know, you're free to leave here, but it's at your own risk. Okay, so I'll see you guys later.